Multiplying radical expressions. So we're going to have a look at how to deal with radical expressions when we're multiplying them together. And we're going to treat them almost exactly how we've learned how to do polynomials, or we are going to treat them how we do polynomials, with the exception that the variables are radicals, and there is some work that we can do with the radicals. When you're multiplying them, you'll multiply the coefficients together, just like if you were to do like 5x times 2x. You multiply the coefficients together, and then you multiply the polynomials together. In this case, you get 10x squared. With an radical expression, you're going to do a similar thing, but when you multiply the two radicals together, they're going to combine together, and you may be able to simplify them after. So let's go into it. So multiplying, simplify where possible. So let's try this one. If we have 5 root 3 times 2 root 2, you multiply the two coefficients together, and we'll do all of the writing to start, and then times root 3 times root 2, and we'll eventually cut this down. But 5 times 2, that's 10. When you have two roots that you're multiplying together, you can combine them under one root without drawing the other root. And voila! We can combine those and we get 10 root 6. If this root 6 is something that you can further simplify, you need to further simplify it. We'll see that in this case. So the next one, 5 root 3 times root 6. Multiply the coefficients together. 5 and 1 just leaves us with 5. And then underneath the root, we're going to get 3 times 6. That is combinable, and we get root 18. Now, root 18 does have a perfect square part of it. That's something that we can simplify out afterwards. So 18, its prime factors are 2 times 3 times 3, or 2 times 9. The 9 is going to be our perfect square. Just like I showed you guys before, you can pull apart the 18 using a factor tree if this is more comfortable for you to really narrow it down to see if you have any perfect squares. You're just looking for pairs. Any pair of factors is a perfect square. So let's separate the 9 root from this. We have 5 root 2 times root 9. Root 9 is a perfect square, so it's going to simplify to 3. Now we're multiplying root 2 by 5 and 3. That's the same as 15 root 2. And that is the simplified form of that. On to the next one. When you're multiplying a binomial, just use the distributive property. You're going to multiply this inwards to both of them. So negative 2 times 4 is negative 8. 11 times 2 is cube root 22. Do note that this is a cube root. And then negative 2 times negative 3 cube root 3 is going to be plus 6. And then 11 times 3 is cube root 33. If these have the same root, you can combine them. You would need to have the a perfect cube to pull out of them, and there's no perfect cubes. So root 22 and root 33 are two different values. There's nothing further that you can do with that. That's as far as that one goes. When you're multiplying two binomials together, just like you're doing two binomials with polynomials, you multiply each term with the others. So this 4 root 2 is going to multiply with the root 7 and the negative 5 root 14. Same with the 3. The 3 is going to multiply with the root 7 and the negative 5 root 14. So there's 4 multiplications to do. There's going to be 4 terms to work with at the end. So 4 root 2 times root 7 is going to be 4 root 14. And 4 root 2 times negative 5 root 14 is going to be negative 20 root 28. Now the 3 times root 7, that is plus just 3 root 7, because it's 3 times root 7, so 3 root 7s. And then 3 times negative 5 root 14 will be negative 15 root 14. Now any of these we can simplify. We'll notice they're all multiples of 7. Perhaps there's some stuff that we can do with that. We would have to be able to pull out perfect squares if we can. Otherwise we just have to combine them with other ones. So this 4 root 14 and negative 15 root 14, those two are combinable. So let's do that. So we'll put them next to each other for this line. Feel free to just combine them in one go. Now root 28 does have a perfect square involved with it. Root 7's a prime, so that's as low as that one's getting. Root 28 does have a perfect square, specifically 4. 4 times 7 would give you 28. So let's split the 28 into its 2 roots, one of them being a perfect square. So turn that into root 4 times 7. And we're going to separate out that 4 and simplify it, plus 3 root 7. These two can come together now. 4 of something minus 15 of those same things will leave us with negative 11 of those, specifically root 14s. And this root 4 is going to turn into 2, so this will turn into negative 20 times 2 root 7. And we still have 3 root 7 here. Negative 20 times 2 is negative 40. So minus 40 root 7s. And now we are able to combine our root 7s together. We have negative 40 of something plus 3 of those things will leave us with negative, will leave us with negative 37, sorry, root 7s. And there we go. For this one, it's not 2 binomials. It is a monomial times binomial. So we'll use the distributive property and multiply it inwards. So negative 2 times 4 will be negative 8. And then 11x times 2x cubed. We're combining together our ideas here. Still going to go underneath one root. Let's write out the whole thing. 11x times 2x cubed. And then we're also going to do this negative 2 root 11x times the negative 3 root 3. So negative 2 times negative 3 is positive 6. The root, underneath the root, we're going to have 11x times 3. Lots more work to do here. So negative 8 underneath here. Multiply the coefficients together and we'll get 22. X times x cubed is x to the 4th. Note that is a perfect square. Plus 6, and then 11x times 3 is going to be 33x. So we are going to, 22 doesn't have any perfect squares associated with it. Its prime factorization is 11 and 2. There's no pairs there. So the 11x4 though, it does have a perfect square, x times x, or x squared. X squared times x squared gives you x to the 4th. So we can pull that out. Let's separate the two of them, and let's have x to the 4th times root 22 plus 6 root 33x. So the x to the fourth, the square root of that is going to be x squared, so 8x squared root 22. And nothing further that we can do here. 33 is not a perfect square, and neither is x. So 6 root 33x. Onwards. Let's include our exponent laws. So how do we manage multiplying exponents together? We're multiplying two of these same things together. This is actually kind of a really interesting strategy when it comes to perfect squares. This idea of multiplying two radicals together of the exact same value, watch what happens. If I have root 4 times root 4, that's the same as root 4 squared. If we combine those underneath the radical, we'll have root 4 times 4, underneath one radical I should say, and that is root 16. If you multiply any two radicals together of the exact same value, oops, we don't need a root now, root 16 being a perfect square, it has to be because we're squaring it, is going to essentially eliminate the square root. This is an interesting strategy that we're going to visit a couple times in the future of this unit. So next we have negative with the negative outside times root 4. Treat that negative on the outside as a negative 1. If it's inside the brackets, it's different. So, sorry, this one's inside the brackets, this one's outside the brackets. So if we are squaring negative root 4, the negative of root 4, that's the same as doing negative root 4 times negative root 4. Now imagine multiplying these two coefficients together. This is a negative 1, this is a negative 1. That's the same as positive 1. The negative times a negative, any negative times a negative cancels out the negative. So negative 1 times negative 1 is just positive. So underneath the root, though, we still have the 4 times 4, which we know is 16. Root 16 is still 4. Note that we get the same thing. And that's part of our understanding about squaring anyway, that a positive and a negative will, squared value will give you the same outcome. When the bracket's on the outside, though, this square doesn't apply to the negative. It's just what's inside of here. So we are going to keep this set of brackets, and this is the negative of root 4 times root 4. It's what's inside the brackets that gets squared. So that does change the outcome here. Root 4 times root 4, we already did that one. It's going to work out to be 4. Now the negative of 4 is negative 4. Where the negative is matters in terms of how to square it. If the square includes the negative, then that negative needs to be squared as well. If the square doesn't include the negative, that needs to be applied after you've done your exponent work. So 2 root 4 squared, we are going to do 2 root 4 times 2 root 4. Just like we learned before, we're going to multiply the coefficients together. 2 times 2 is 4. Root 4 times root 4 is root 16. We know that that works out to be 4. Root 16 is a perfect square. Keep doing that. Let's see if I can stop doing that. 4 times 4, and our final answer here is 16. So finding area, different from perimeter when we were learning before, when we're adding up all the sides, now we're going to multiply them together. Notice that this is going to be two binomials multiplied together. So area is equal to length times width. let's define our length and our width. It doesn't matter which one we choose. Let's go like this. So our area is going to equal 4 plus root 6, and then we're going to multiply that with 7 minus root 6. So with multiplying binomials, you multiply each term with the other set of brackets. We're going to distribute the 4 to the 7 and root 6, and we're going to distribute the root 6 to the 7 and root 6. So we're going to have 4 terms to deal with, and we'll see if we can simplify anything at the end. 4 times 7, nice clean 28. 4 times negative root 6 is going to be negative 4 root 6. Root 6 times negative root 6 is going to be negative root 36. Oh, I jumped ahead. Root 6 times 7 is going to be plus 7 root 6. Doesn't really matter the order that you write them. So combine together whatever you can, solve whatever you can. The root 6 is shared. There's 2 terms that have a root 6, so we can combine together their coefficient. We are adding them. So negative 4 and plus 7 is going to give us the 3, 3 root 6. And we still have the 28. This square root of 36, that's a perfect square. Again, anytime you're multiplying together the exact same radical, or sorry, if you're multiplying together a number with the same radicand, you are going to end up with a perfect square. So root 6 times root 6 is going to be 6, but it's positive times a negative, so it's negative 6. So the root 6, if we can simplify that, we should. Root 6 is not simplifiable. Its prime factorization is a 2 times 3. There are no pairs there, therefore no perfect squares. That is as low as we can go for that one. But 28 and 6, we can combine that. 28 minus 6 is 22. So the area of a rectangle with side lengths 4 plus root 6 and 7 minus root 6 would have an area of 3 root 6 plus 22. So for a square, you have all 4 sides that are the same, so it's still area, but we just designate that side length. The area of a square is the side length squared. So let's substitute in our side length here. This is going to be 2 root 18 minus root 27. We could do some simplifying here, but why don't we save that till the end? That's squared. So let's rewrite that. Let's expand it. Minus root 27. And times another one, 2 root 18. Minus root 27. And now we multiply each of the terms with the others. So 2 times 2 is going to be 4. Root 18 times root 18, we hopefully picking up by now. It's going to be a perfect square. We're squaring root 18, so it's just going to turn out to be 18. 2 root 18 times negative root 27, though. So 2 times negative 1 is negative 2. And root 18 times root 27 is, well, it's challenging me. 20 times 27 would be 540. Minus 2 27s minus 54 would be 484. So root 484, 46, 486. Sorry, almost made a mistake there. And then negative 1 times 2 is going to be negative 2 again. And then root 27 times 18, we just did that one, is root 486 underneath the radical. And then root 27 times root 27, and negative times negative is positive. We're squaring that number. 27 times 27, root 27 times root 27 is going to be 27. Let's do some combining here if we can. So 4 times 18 is 72. And 27, let's put them together so that we can combine them after. Now negative 2 negative 2 root 486 and negative 2 root 486 is going to be minus 4, so we're subtracting these two so we can combine them. If you have the same radical, you simply add or subtract the coefficients, and that's still root 486. So that 486, we need to see if there's any perfect squares in there. Let's do a factor tree for 486. Let's split that into, that would split into 243 and 2. And then 243 is divisible by 3. That's going to be 81. And 81, we know that's a perfect square of 9 and 9. We're going to be happy with leaving those factors like that. We can split it into 3 and 3, but we got our perfect square there. So 486 is the same as 2 times 3 times 9 times 9. So let's do that. 72 plus 27 minus 4, and then underneath the root, we're going to have 9 times 9 times 2 times 3. The 9 times 9 we know is 81. The square root of 81 is 9. So let's pull that 9 out. 72 plus 27. And then minus 4 times 9. And then underneath the root, we still have the 2 times 3, which is root 6. One more line, and we've got it. Let's actually add these together. 27 plus 72 is 99. And then minus 4 times 9 is 36 root 6. 6 doesn't have any further things to simplify from it. So conjugates. Conjugates are interesting. As I was mentioning before, multiplying the same thing with itself eliminates the radical, and that can be a really interesting strategy of eliminating radicals from certain places in an equation where you really don't want a radical. So let's just have a look at how polynomials behave when you multiply conjugates, and perhaps this will give us some insight into how radicals will behave. So multiply everything in here, distribute everything in this term with everything in this term. So x times x equals x squared. X times negative 3 is negative 3x. 3 times x is 3x. And 3 times negative 3 is negative 9. Negative 3x plus 3x cancels out, bump, and we're left with x squared minus 9. So when you multiply conjugates, look at what you get. You're squaring this term, and you're squaring this term, but with a negative value. And you can jump right from the binomial multiplication into your answer that is essentially a trinomial, but with a middle term that equals 0. And this will be useful. Notice how these x's, we've been treating our radicals as x's, like say a root 2, but by doing the conjugate of it, we end up squaring it, which means no matter what radical we have here, if it's root 2 squared, we'll eliminate the radical and get just whole numbers from it. So by multiplying a radical by its conjugate, you eliminate the radicals. Let's see what that looks like. So write the conjugate of each, then multiply each pair. So if I had 4 root 6 plus 3, its conjugate would be, let's just jump right to the multiplying, its conjugate would be 4 root 6. I treat this like 4x plus 3, and 4x, but 4 root 6 minus 3. That is the conjugate, that is the conjugate of 4 root 6 plus 3. So let's do that multiplying we were talking about. Let's distribute both the terms in this binomial with both the terms in this binomial, and you'll see the result is no more radical. So let's do 4 times 4 is 16. Root 6 times root 6 is going to be root 36. Note the perfect square. 4 root 6 times negative 3 will be negative 12 root 6. 3 times 4 root 6 is positive 12 root 6. And 3 times negative 3 is our minus 9. 16 times root 36. That root 36 is a perfect square. Turn it into its whole number. Root 36 is 6. Now negative 12 root 6 plus 12 root 6, that's just gone. They eliminate each other. They equal 0. And then we're just left with minus 9. 16 times 6 is 96. Minus 9. And 96 minus 9 is 87. Notice multiplying a number by its conjugate eliminates those radicals, and you're just left with whole numbers. That's a useful strategy. We'll explore that more later on. So the conjugate of the next one, you're going to subtract, so negative 2, try again, negative 3 root 11 plus root 2 multiplied by negative 3 root 11 minus root 2. Distribute. Negative 3 times negative 3 is 9. 11 times 11 is 121, so underneath the root is going to be a perfect square every time. That's root 121. Now negative 3 root 11 times root 2, negative root 2, make sure I emphasize that a bit. Negative 3 times negative 1 is plus 3. 11 times 2 is root 22. Now on to the next one. So root 2 times negative 3 root 11. 1 times negative 3 is negative 3. 2 times root 11 is root 22. And the last one, root 2 times negative root 2 is going to, root 2 times root 2 is 2. Or we can keep it under the radical and say 2 times 2 is 4. The square root of 4 is 2. A positive times a negative is a negative. So negative 2. This 121 is a perfect square. 9 times 11. And then 3 root 22 minus 3 root 22 will be 0. Minus 2. 9 times 11 is 99. Minus 2 is 97. On to the last one. The conjugate of 5 root x minus root y is 5 root x plus root y. So 5 times 5, 25. X times x is x squared. Again, even though it's a variable, perfect square. 5 times 1 is 5, so plus 5. X times y is xy. That's the best we can do there. On to the next one. Negative 1 times 5 is negative 5. Y times x is root xy. And then y times y is, or sorry, negative times positive is a negative. Y times y is y squared. All right, so 25, the x squared is a perfect square. The square root of x squared is x. So 25x, and then 5 root xy minus 5 root xy is going to be 0. 5 of anything minus 5 of those same things is 0. And then minus, and then the square root of y squared is y. So minus y. Note that we square this number, we square this number, and we keep the negative of the second term. And when you're multiplying conjugates. That's it. Thanks for joining.